speaker is Bertrand Deroin from the CNRS and Université de Cergy-Pontoise. He will talk about Jouanolou-Type foliations and algebraic surface.
Thank you. So, vous vouliez faire la fête sans moi? I am very happy to be here, and I am very happy to give this talk. And I try to think about what I am going to say to Franck. And I remember that, in fact, what I could say, many things, because Franck, you inspired me a lot in all what I did, I think, your works, and it began in, I think the first time I encountered you was in Tordesillas. Do you remember? You gave a lecture on, maybe on your text on the singularity, on the pseudo-group d'une singularité. And so this was the occasion for me to understand these holonomy maps and monodromy phenomenon for foliations, and I liked it a lot, and it was very good moment, I think, very pleasant, very friendly. And I think it's going to be related because my talk I chose to speak about dynamics of foliations, where the holonomic subgroup is extremely important. And so I am going to speak about so foliations on compact algebraic surfaces, and I will try to, so maybe the talk is going to be a lot of questions and few results, the foliations I am going to consider are generic foliations. I am not going to focus on particular examples, but on the generic ones. So typically singularities are going to be hyperbolic, and there will be no invariant algebraic curves. We are going to be in this domain. And the main concerns of the talk is going to be on the modular space of holomorphic foliations on complex surfaces, to study the dichotomy, structural stability versus bifurcation. Okay? So, definition in a holomorphic family of holomorphic foliations. Maybe I will just say afterwards, just foliation means holomorphic foliation on compact, let me put algebraic, but or complex, sorry, compact complex surfaces. So say to fix ideas, so we have a family of complex surfaces, x lambda, that depends on the parameter, foliations f lambda, depending also on the parameter, and the parameter lives in some complex manifolds, lambda. Okay? So a parameter lambda naught is structurally stable if there exists a neighborhood of lambda 0 in lambda neighborhood such that foliations x lambda, f lambda are topologically conjugated for lambda in the neighborhood. So they look the same from a topological point of view. And also, in general, we ask in the definition, maybe there are several definitions of structural stability. We also can ask that the conjugacy is close to the identity. We generally do that. I will not write this. And so we have the stability locus. So this is a set of parameters that are structurally stable. This is an open subset. This is a set of structurally stable parameters. So this is an open subset. It's open. And there is the complementary, which is called the bifurcation locus. Just this is the terminology. This is a complementary. Or the complement, sorry, complement of stability locus. And it is a closed, this is a closed subset of lambda. Okay. So there are two main examples I would have to discuss, and I will try to discuss more general examples in the talk. But so there is a first example, which the moduli spaces of Riccati foliations. So if you pick a genus, so G is an integer, and you pick a number of another integer, a number of points, and you can form. Actually, I would have to get the details of that. Let me just say that there exists such moduli spaces. In fact, I would like to really understand how we construct this moduli space. I think it exists. This is the moduli spaces of Riccati foliation. I will define what it is. I think we saw it a lot in various talks this week. Over a base of genus G, and with n vertical fibers, vertical leaves. And I will be assuming that the poles are symbols here. Okay, so you have, so definition of a Riccati foliation, you have a fibration. So X, the surface, is a fibration by rational curves over some base, B. So here's a genus, so we have a fibration, pi. And we have a certain number of vertical fibers, so n, exactly n vertical fibers. The genus of B is G. And so these fibers contain some singularities, and the other fibers are transverse to the foliation. So the foliation is just transverse. And so Riccati comes from the fact that in certain coordinates, what's the name here? So Z is a coordinate on the base, on B, and T is a coordinate on the rational curves. So those Riccati foliation takes the following forms, where A, B, and C are meromorphic functions with simple poles. Okay? And here, why I'm speaking about this moduli space is that in this moduli space, it displays a non-trivial dichotomy in structural stability locus and bifurcation locus. And in fact, it was studied by Sullivan. I will come back to the result of Sullivan later. But maybe there should be many names here. Alfors, Bers, Poincaré, I don't know. Okay. And probably many more there. So there is a non-trivial dichotomy okay, where here, in fact, there is a, so this is where Sullivan came into the game. It is the stability locus. Sullivan proved that it is made of quasi-Fuchsian, so Riccati equation with quasi-Fuchsian holonomy when there are no vertical fibers, and Riccati foliation with Schottky holonomy when there are some vertical fibers. So quasi-Fuchsian is when n is equal to 0, and Schottky holonomy when n is positive. Okay, so quasi-Fuchsian holonomy means that the holonomy, so the monodromy group of this differential equation here, so this is a group acting on the t coordinate. So we have t here in P1. You can look at the monodromy group, and quasi-Fuchsian means that there exists a topological simple closed curve that, in fact, it's I don't remember the name. Anyway, you have this topological curve that separates the sphere in two domains that are disks, and on which the representation acts properly, discontinuously, and without fixed points. So this is the case of a quasi-Fuchsian holonomy. The case of a Schottky holonomy, you have a Schottky group acting on the sphere. We have seen in various talks also Schottky group. You have a limit set, which is going to be a counter set, and the group is free. So the group here is just the fundamental group of the base minus the points, and you have a limit set which is invariant, and this is structurally stable. So those two examples are structurally stable, and in fact, Sullivan, a very important theorem of Sullivan, proved that those are the only ones in this context. Okay. Okay, so this is the first example, very important and inspiring example to have in mind, and the other example is of a non-trivial dichotomy is the moduli space of foliations of degree 2 of the projective plane. So this is moduli space of degree 2 foliations on P2. And here we also have, so this is a 6-dimensional manifold. I am quotienting by the action of PGL3. I really take the moduli space. This is a 6-dimensional space. And in this space, we have a non-trivial dichotomy, which is probably true for any degree. In fact, we know how to prove that in degree 2. So there is a stability locus which is non-trivial, and there is a bifurcation locus which is also non-trivial. So the fact that there is a non-trivial bifurcation locus, Georges described yesterday this work by Franck and Giulio. So this is Loray and Bello proved that it is non-trivial. I will describe more in detail just in a moment. this work. And the stability locus is non-empty. This is a work that we did with Aurélien Alvarez 5 years ago. And in fact, we proved that the Jouanolou foliation which is a projectivization of this simple differential equation on C3, homogeneous differential on C3, in the x, y, z coordinates. So this projectivization gives an example of a structurally stable foliation on P2 of degree 2. And in fact, conjecturally, if you replace 2 by any d, it will be structurally stable. We verified numerically that it holds for d less than 6, I think, and we really believe that it is true. But let me just state a first problem. And before stating this problem, I would like to describe more in detail this Loray-Rebello. Because, as was saying George yesterday, in fact, this is not just that they prove that there is a non-trivial bifurcation locus, but Franck and Giulio proved that, in fact, there is a non-empty, so it has non-empty interior. And more than that, they proved something quite crazy, which very strong property. You see here, in the context of Riccati foliation, when you take the bifurcation locus, in fact, this bifurcation locus, it has non-empty interior also. Okay? And you can see there are some pictures. I have not, I'm sorry, I will just, if you are interested, you can look at the website of Émilie Dumas. She produced a lot of pictures of this stability, of these decompositions that are very interesting. And you can see that in this context, the bifurcation locus is really of empty interior. This is not at all like in the Mandelbrot set, which has empty interior. Here, you have, I mean, the bifurcation locus in the rational maps. Here, you really have a non-empty interior. And in fact, the points corresponding to the interior of bifurcation are the representations which are non-discrete image, and generically they are dense image. Okay? So of course here the Slice foliation preserve a projective structure. I mean they are transversally projective. And what Loray and Rebello proved is that they produced a non-empty open set of foliations where the holonomy pseudogroup is dense in the whole pseudogroup of all B holomorphisms. That was previously, there was a previous article with Lius and Béliard of Franck for differential equation on the plane that preserve a line at infinity. Okay, so maybe I will say it like this. So let's call it Loray-Rebello regime, and just say that the holonomy pseudogroup is dense in the whole, is the pseudogroup of all local B holomorphisms. Okay, so to be more specific to understand well, because it is very important and completely unbelievable in a sense. This is that you have a pseudogroup, your pseudogroup of your holonomy pseudogroup of your foliation, sorry. So you have a Riemann surface, so in fact, concretely, it is a certain union of disk, finite union of disk. You have a pseudogroup, which is a holonomy pseudogroup of your foliation. So the return maps given by the holonomy maps of your foliation. And in fact, if you take any pairs of points, x and y, so say this Riemann surface, this union of disk, I call it T. This is a transversal space. You take 2 points in T, any pairs of points. You take any biolomorphisms, germ of biolomorphism defined at x that send x to y. There exists an open set around x where this germ is defined, and you can approximate this map by a uniform limit of holonomy maps of your foliation. Take any germ. So this is the property that implies minimality of the foliation, so all leaves are dense, ergodicity of the foliation, and it implies a very strong property of instability, namely that a very strong form of rigidity, okay, that I don't want to make. But in particular, this implies that this Loray-Rebello regime is a subset of the bifurcation locus. Okay? And so the first question I would like to ask is I think is very interesting to try to understand more in detail this bifurcation locus for foliations, at least of P2, but maybe more in general. So let's say yes. So is it true that Loray-Rebello open set, this is an open set, it is equal to the interior of the bifurcation locus? I think it is true. This is true in the case of Riccati foliation, where you don't have this regime because you have a projective structure which is invariant. But in the context of Riccati foliation, this is true that if you take a point in the interior of the bifurcation locus, then no, maybe this is not that. Sorry. I'm sorry. This is not the good. This is not the good. Yeah, no, I'm sorry. This is not in that direction. So you take the closure of the Loray-Rebello regime. So you take the, and this is in that direction, I think. So this is in that direction which is true in the context of Riccati foliation. So namely, if you take any representation in the bifurcation locus, you can approximate it by a representation with dense image, whose holonomy group has dense image. I think this is very important question, I think, but probably very difficult. I don't know. I have no idea of how to prove such a thing, but Okay, another question, which is maybe more tractable, and I'm going to put here to understand more in detail this bifurcation locus and also Loray-Rebello component, is that Loray, so Franck and Julio proved that there exists these non-empty open subsets in moduli spaces of foliations of the projective planes, and also, in fact, as George was saying yesterday, in any dimension, but I'm going to stay in the context of surfaces here. But it should probably be true that, in fact, it holds in much more general moduli spaces on any complex surface, not the projective plane. There is no reason a priori. And so probably, I put question, but I think maybe it should be better conjecture, is that are there non-empty Loray et Bellon open subsets in moduli spaces of more general complex surfaces. And probably it is true that if you take a moduli space of foliation with a very ample cotangent bundle, which was defined by Laura and Gomez-Mont, which was studied in their work extending Ilyashenko's theorems, I believe in those moduli spaces it should be true, this statement. So I think most moduli spaces of holomorphic foliation will contain these kind of things, in a sense. Most you have to define maybe what it is, but I really believe that that will be true. Okay. Now I would like to, again, I don't know how to prove this, but I think it is more tractable. Maybe you just follow the proof of Franck and Giulio and adapt a few things, and it works. Now I would like to speak more about, so I spoke about maybe the structure of this bifurcation loci. I would like to speak more about these stability loci. And in fact, with Aurélien Alvarez, we developed a theory, which is the title of my talk, so of foliations that we called Jouanolou-Type, because in fact, we just extracted what is very important in the proof of the stability, structural stability of Jouanolou foliations. And so we developed a kind of theory, a general definition of what are those foliations, and studied some of their properties. So let me just start with that. I will go there. So here's the definition. So a foliation. So it is holomorphic foliation. F of a complex, compact surface is, so, Jouanolou-type if, so three conditions, but the important condition is the first one, which is the following. There exists a metric, a Hermitian metric on the normal bundle of the foliation. So when you take a metric on the normal bundle, you can think of this as permitting you to measure what is the infinitesimal distance between leaves. So you have got functions defined on the leaves that tells you what is the distance of infinitesimal leaves. Okay? And also I have to say here that this normal bundle can be extended. We are in a complex surface. It can be extended to the singular set. When I'm speaking about a metric here, I'm speaking about a metric that extends as a smooth metric on the singular set as well. But this is kind of details. I don't want to enter into that, but I just say it. So there exists a metric. So that the critical points of the infinitesimal distances between leaves, infinitesimal infinitesimal distances between leaves are non-degenerate and local maxima. This is the local maxima, which is very important. Okay? This is a Hermitian metric on this line bundle. So NF is a line bundle, and this is a Hermitian metric on that line bundle. And so let me just do a picture. So you have your leaves. So locally there are disks. So let me just write like a plaque in a leaf. This is a disk. And the leaves nearby those one, so maybe here, so this infinitesimal distance is defined on a leaf, in restriction to a leaf. Okay, it's not well defined. It's well defined up to multiplication by a real number. But the leaf which is nearby is going to look like something like this. So, but here, there is a local maxima here, and the same for the leaf below. So you have a kind of picture like that. Okay, so the leaves. So here you see you have a critical point of the infinitesimal distance. You have a local maxima, but so when you see a critical point for the infinitesimal distance, you have this picture. Okay. So maybe in coordinates, if t equals constant defines the foliation, your metric is something like this. So this is the metric. And what I am saying is that phi restricted to a leaf. So this is the log of the infinitesimal distance. So I want that this has non-degenerate local max critical points. Okay? And if you have this, so this is the first condition. Let me just write the two others. So there is one condition which is kind of evident because we are trying to find a condition for structural stability. We have to ask that the singularities are also structurally stable, which we know it is equivalent as being hyperbolic. So hyperbolic singularity, we ask that. And to have hyperbolic singularities says that these sets of critical points for the infinitesimal distances is a surface, a real surface, which is far away from the singular set of the foliation. It's really. And there is a third condition which is kind of technical, and maybe it can be dropped, but we don't know. There is no elliptic leaf. Well, it's not a big deal. So this is the definition. A leaf which is bielomorphic to an elliptic curve. And in fact, we can, as I said, those are the conditions that permits to develop the arguments that we use to prove that Jouanolou foliations are structurally stable. Namely, we have the following theorem. So maybe I'm going to define B. This is this set of critical points. So this is a surface, a real surface, which is transverse to the foliation, and which is given by the sets of points where these functions have critical points. Okay? This is a transverse surface to the foliation. Infinitesimal distances. And so the theorem is that a Jouanolou-type foliation is structurally stable in any holomorphic family in which it belongs to which it belongs. Oh, I don't know how to say it. Yeah. Stable. And moreover, a non-trivial Fatou-Julia decomposition. So in particular, it is not so it is not minimal, it is not ergodic. In fact, the Fatou component, we prove this is the reason why I introduced the B. We can prove that the Fatou component, as in Jouanolou foliation, it is a fibration, a disk fibration over B. This curve there, over there. Okay? And yeah. And the proof, let me just say a few words about the proof, because there is, this is a little bit, this is not just copying the same argument as the one for the Jouanolou foliation. There is a new thing, which I think is very interesting in the proof, just for the proof. So the proof is find real vector fields. So it is not holomorphic, it's real. Tangent to F, and with good enough, I will not be very, very specific here, hyperbolic properties. So hyperbolic means that there is a decomposition of the tangent bundle of X, the real tangent bundle of X, with a strong stable distribution, which is contracted exponentially by the derivative of the flow, and a strong unstable distribution, which is expanded exponentially by the flow. And those two distributions plus the direction of the flow gives you a direct sum decomposition of the tangent bundle. Okay? And when you have hyperbolicity property, you have some stable leaves. And we want that the stable leaves are the foliation given by the leaves of the foliation F. So with weak stable foliation equal to F. And in fact, because we know that hyperbolic flows are structurally stable, when we have this property, it will imply quite easily, I mean, the structural stability of the foliation F. This is really the idea. Now, how to find the flow? So the flow, you just take the gradient flow of the function phi. So this flow is going to be, so you want a flow so that the leaves are exactly the weak stable leaves of, I mean, the leaves of foliation are exactly the weak stable leaves of the flow. So you want that in the leaves of the foliation, so if I take F, a leaf of F, the flow, I want that its trajectories converge exponentially between themselves. And transversally to the foliation, I want an hyperbolicity behavior in the opposite direction, namely, I want a picture like this, okay, in the transversals. So a good way is to take, for the flow in the leaves, to take the gradient of the infinitesimal distance in between the leaves. I will automatically get the transverse hyperbolicity. So you can define first this flow. You take the gradient of the log of the infinitesimal distances. It's well defined, and you get directly the hyperbolicity, transverse hyperbolicity that you want. The point is how to prove what happens in the direction of the leaves. So in the case of Jouanolou, there is a kind of miracle, which is that we can find a metric like that, which is subharmonic. And when we take the gradient, automatically we will get the hyperbolicity on the leaf directions. But in general, we don't want to put that in the definition. And in fact, we don't need to put that in the definition. What we prove, and I will just say that, it's kind of complicated, we prove that we can gain hyperbolicity along the leaves also. We can modify the gradient by stretching the trajectories conveniently in a way that we get also the hyperbolicity along the leaves. And so we can prove this theorem. And let me go to the next question. And I think, how much time do I have? 8 minutes, okay. So let me go to that question. Yeah, here. So I think this one is very so is it true that the converse is true, namely structurally stable and I will put something because it is evidently false on sufficiently large moduli spaces. Like, for instance, for holomorphic foliations on P2 of a given degree of Jouanolou-type. So this is a question. Why sufficiently large moduli spaces? Because there are some foliations on complex surfaces that are rigid. This was the reason why I asked you this question, George. For instance, Hilbert modular foliations are rigid, so they are structurally stable. We cannot deform them at all. So they are structurally stable, but they are not at all of Jouanolou-type because they are Riemannian. You don't have any hyperbolicity in those foliations. So this is the reason why I put sufficiently large moduli spaces. I don't know what should be the good condition, but you have to get enough possibility for deforming the foliation to have a hope to get such a condition. And why I ask this question, this is not just because we can, when we prove one implication, we want to know if the other one is true. Of course, we want to know, but this is not just that. This is that the answer is positive, yes, for these moduli spaces of Riccati foliations. And this is quite hard. This is the Sullivan stability theorem. This is very that I spoke about before. And these kind of results are very difficult, are known to be very difficult. For instance, in the context of rational mappings, this is a hyperbolicity conjecture, which is still known. So it is probably kind of question which are very, but it is very well possible that this is true. In fact, such a statement like this. And I have 4 minutes, and just I wanted to say that. We have another result, which we found a little bit disappointing a priori, because we wanted to, we would really like to have more examples of structurally stable foliation like Jouanolou, but in other complex surfaces and etc. And this theorem tells us that, in fact, the variety of surfaces that can carry a Jouanolou-type foliation is kind of restricted. In fact, we proved that. So we have to assume this algebraic. So an algebraic compact complex surface carrying a Jouanolou-type foliation is ruled. So for instance, if you take a torus or K3 surface or general type surface, there is no Jouanolou-type foliation on that surface. And so I don't want to enter into the proof of that, but it was just, I just say that to get the occasion to ask the last question. I think it's interesting. So maybe if you believe to the positivity of the answer to the last question, that would say something like this, like question, last one. Is it true that if X is not ruled, the stability locus on moduli spaces of foliation on X is NT. Or in other words, is it true that the bifurcation locus and maybe a Loray-Rebello component is dense in the whole moduli space in those examples? Take, for instance, a torus, take moduli spaces of foliations that are given by nice theta functions. You take those moduli spaces, maybe there you have the Loray-Rebello component is dense in the moduli space. Okay, I'm done. Thank you, Franck. Happy birthday.